Hi, welcome to videos on analog communication. So this is the ninth video. So in this topic we'll see the SSB modulation and demodulation. Let us see the theory part of single sideband suppressed carrier modulation. So here we're going to have operating signal m of t. So having AM as the amplitude and FM is the frequency of the modulating signal. And considering the carrier signal, which is C of t, having a magnitude of AC with a carrier frequency of Fc. So the modulated signal of a SSB includes the product of m of t and C of t, either the addition or subtraction of Hilbert transform of message signal and the Hilbert transform of the carrier signal. So the plus actually give you the lower sideband, and the subtraction of m of t, C of t with m cap of t and C will give you the USB part of SSB, that is upper sideband and lower sideband. S of t considering both lower sideband and the upper sideband. Suppose if you see now, okay, this is now single sideband suppressed carrier. So we're going to have this component. Suppose if you take the algebraic sum of those two, we're going to end up with the lower sideband. So the subtraction of that will going to give the upper sideband. So this is a spectrum of the SSB, SC, LSB and USB. So as you can see here, so this doesn't have a carrier component. This will have only the lower sideband. So and of course for USB we won't have only the upper sideband. We will see the LabVIEW implementation of the same SSB SC modulation. Here we are trying to demonstrate modulation of both upper sideband as well as lower sideband. So when it comes to demodulation, we'll be doing only one demodulation, either lower sideband or upper sideband. You can see now here we have a product modulator being represented by a multiplier, and there is one more multiplier here. So this is going to give the in-phase component of m of t multiplied with the C of t. A 90-degree phase shift its message signal, and the carrier signal will going to give you the quadrature component of the S of t. And the addition of in phase will going to give the lower sideband. So where you can see the spectrum of it, and of course you can see the graph also. Similarly, the subtraction of in phase and the quadrature phase will give you the upper sideband. So we will visualize both the waveform as well as the spectral of the SSB modulation, that is both LSB modulation as well as USB. We'll actually go to the LabVIEW simulation simultaneously, that is modulation as well as demodulation. Let us see the demodulation also. This we have. This is the SSB demodulation process. So it is also a coherent demodulator. It requires a local oscillator whose frequency is exactly equal to the carrier frequency that is used at the modulation process. That is multiplied with the upper sideband and the lower sideband, and that is passed through a low pass filter. The low pass filter cutoff frequency should be such that it should pass only the message signal, but it should suppress the high frequency carrier signal. And of course you can have a spectrum to observe the message signal spectrum, as well as you can have a graph indicator to see the sine wave. So now let us to LabVIEW and try to find out, okay, how does both modulation and demodulation look like for an SSB modulation scheme. Block diagram of implementation of the LabVIEW. So we can specify the frequency. We have actually selected the sampling rate of this carrier signal as 10 megahertz. Let us have the sampling rate of all the signal sources as 10 megahertz, so that it will not create any problem in demodulation. That means I can go with a carrier frequency of even up to 5 megahertz. That's the reason why we went up to 10 megahertz here. So let me close this. So let us observe the block diagram of this entire modulation demodulation. So this is a carrier signal, and we have a message signal. You can see there is a multiplier. So this actually multiplies the carrier signal and the message signal. So this multiplier will actually is what in phase component of that SSB. Now I'm going to have the Hilbert carrier signal. The difference between this signal and this signal source is, here the phase of this is by default 0 degrees, whereas the phase of this Hilbert carrier as well as the Hilbert message signal is made as 90 degrees. So that's how we differentiate the in phase and the quadrature phase components. You can see now there is one more multiplier which will actually give you, one second, so let me just do undo. So now this is the second product modulator which is giving the quadrature component, and that is being added here. Suppose it is in phase and the quadrature phase component, if you add it, we'll actually get the lower sideband. The subtraction of in phase and quadrature phase will give you the USB. You can see here this corresponds to USB part of the suppressed that is suppressed carrier LSB USB component. Now this happens to be the suppressed carrier single sideband, that is the LSB. So here we have both the modulation technique, both the modulation component, that is both LSB as well as USB. Whereas coming to demodulation, so here we have taken the USB part of it, the LSB part of it, that we again multiplied with a local oscillator. So this will going to give the demodulation of the lower sideband. So that is passed to a low pass filter. Of course, you can see what is the cutoff frequency of low pass filter is around 20 kilohertz. So that even when I go up to 20 kilohertz as my message signal, I can able to get back the demodulated signal. So let me have a cutoff frequency of this. So this has got a cutoff frequency of 20 kilohertz. So let us have a look at it. So this is the cutoff frequency. You can see cutoff frequency is taken as 20 kilohertz and the order of the filter is 3. This is fine. And we have a spectral measurement so that you can see the spectrum of demodulated waveform, and of course you can also see the waveform. We are seeing the spectrum of the product modulator, which is going to have one of the message signal and a high frequency component. So let us go to the block diagram, the front panel, and just now conduct the experiment. So this is the front panel of the SSB. So let me run now. So I'm running so now it is running. So we have kept the frequency of the carrier signal as 100 signal as let me just okay, this is fine. Frequency of the message signal is 5 kilohertz. The local oscillator phase is exactly same. The SSB, that is lower sideband spectrum, C of the carrier is 105 kilohertz. So we have the lower sideband situated at 95, and similarly the 105, that is 105 kilohertz. You can see here modulation of the same. So in the we actually multiply this spectrum with the carrier whose frequency is equal to again 100 kilohertz. You can see we're going to have the frequency component at okay, this is the output of the product modulator at the demo of SSB signal, and this is after to the low pass expecting only the 5 kilohertz signal. You can see this is at 5 kilohertz waveform. Suppose okay, this is 101 kilohertz. Of course, you can slightly at least 5 cycles. Let me make it equal to 5 milli. Let me make it as 5m. You can see now you are seeing 5 cycles. Suppose if I change the frequency by hardly 10%, okay, now instead of 100 kilohertz, if I make it 110 kilohertz, now run now. You can see now you're not getting. So let me make the frequency exactly equal to 100 kilohertz. Now you can get back the message. Let us change the carrier frequency, the phase of the local oscillator different from that of the carrier signal. So let me just make it equal to 60 degree. There is no much difference here. You can see when it was at 0 degree. You can see this is fine. Only thing is that there is a slight phase shift here. Even if you make this equal to 90 degree and then again run this, you can see this is from irrespective of the phase difference between the message and the carrier signal. So as long as the frequency of the local oscillator and the carrier signals are same, we're going to get the proper demodulation. So 90. So your modulating signal is 10 kilohertz. We have the low band at 9. This is your demodulated waveform. If you want to see around 5 cycles, make the time period to something like, okay, this should be, let me make it around 0.5 millisecond. Now you can see getting properly 5 cycles. So this way you can able to do the modulation, demodulation. Only issue is that you may not be able to differentiate between the LSB modulated waveform and the sine wave. So this will not it's not as in case of DSPC signal or SCM signal. We are going to have a change in the shape of the waveform, but this almost looks like a sine wave of carrier amplitude. Because you can change the amplitude of the carrier signal as well as the message signal, so that you can write of demodulate version and make it equal to 2. You can see this is the SSB waveform. We don't have electrodes has 1. You will not see any component other than the LSB. If are different, taken the local oscillator magnitude as 1. So parameters also here. If you can see here, if I change, this is because the amplitude of the local oscillator is at the, so let us single sideband modulation. So this way we will to understand the of SSB in 9LabVIEW.